A spectacular example in which the quantum nature of a substance becomes visible by the naked eye is liquid helium-4. Liquid helium-4 has spin 0, hence is a boson. Now in this BBC movie you see what happens if liquid helium is cooled down further by pumping on the gas above the liquid. By pumping on the gas, wild boiling takes place, equal to an observation that you would do if you would have water. By that, the liquid cools down, and if you reach a temperature of 2.1 Kelvin, sudden change happens. The liquid gets completely still and actually is further cooled down. There has been a phase transition happening, and this phase transition we would like to understand. In particular, we will calculate the density of the gas as we change temperature. The density of the gas is given by the number of particles that is contained in the volume. The mean number of particles in an ideal quantum gas is given by the sum on all states k, 1 divided by e to the power alpha plus beta epsilon k minus 1. We assume that we are dealing with a large number of particles, hence the energy eigenstates Ek will be dense, and the sum on all k can be expressed as an integral on phase space. Mean n reads 1 divided by h to the power 3 integral on phase space d3p d3q e to the power alpha plus beta epsilon minus 1 to the power minus 1. Integral on the space variable leads to the volume, and integration on the momentum variable we transfer to spherical coordinates and expressing the momentum as an energy, where we have the dispersion relation, the energy epsilon is equal to p squared divided by 2m. Now from this description we derive the density, small n, depending on alpha and beta, which is given by the mean number of particles per volume, is equal to 4 pi 2m h squared to the power 3/2 integral on d epsilon, square root of epsilon divided by e to the power alpha plus beta epsilon minus 1, where epsilon runs from 0 to infinity. Changing variables further to beta epsilon is equal to x, we obtain a final expression for the density of the bosonic gas as a function of alpha and beta. This expression contains an integral as the last parameter. We see that the integral scales with e to the power alpha plus x. Hence, there is a maximum to this integral, letting alpha be 0. In realizing, we now can calculate what is the maximum density that a bosonic gas can assume, assuming that alpha is equal to 0. And max is just a function of beta and is given by an expression in which there is a prefactor which scales like 1 divided by beta to the power 3/2 coming from the change in variables, and the final integral dx from 0 to infinity square root of x divided by e to the power x minus 1, which is a Riemann integral, the value of which is given by gamma of 3/2 times zeta of 3/2. Taking this result, we obtain the final expression for the maximum density of a bosonic gas when alpha is equal to 0 is equal to n max of beta is equal to 4 divided by square root of pi times 2.315 times 1 divided by lambda thermal to the power 3. It is worth noting how this maximum density scales with temperature. If we let the temperature go to 0, which means beta goes to infinity, we see that this maximum density in this substance goes to 0. This is a very surprising result, although by physical intuition something must be wrong. Although alpha is 0, meaning that without changing the entropy at particles, the density of the particles is limited at low temperatures, which is a clear inconsistency. So the question is, where does this inconsistency come from? To explain this inconsistency, we have to consider the quantum nature of the phenomenon. For any quantum systems, the energy eigenstates are quantized, meaning there are certain energy levels, epsilon 1 till epsilon k, yet there is always a gap between the 0th and the first energy level. Now, when we did our calculation, we assumed that the energy levels are dense and went to a continuous description where, in the classical view, the energy is given by the translation energy of the energy is determined by the momentum of the particles. Now, in the evaluation of the integral square root of epsilon divided by e to the power alpha plus beta epsilon minus 1, we see that at zero energy, there is no contribution of zero energy eigenstate. In order to correct for that omission, we can add the zero energy eigenstate just by hand. The particle density at energy equals to 0 is given by 1 divided by v, 1 divided by e to the power alpha minus 1, which, if we let alpha go to 0, goes to infinity and the density is not limited anymore. Altogether, we obtained the full description of the density of the Bose gas as a function of alpha and beta, given by two terms. The first is 1 divided by volume times e to the power alpha minus 1, which is also called the Bose-Einstein condensate, or the phase 1 of the substance. And the second part, which is 4 divided by square root of pi 2.513 times 1 divided by lambda thermal to the power 3, which describes the normal state of the substance, also called phase 2. So what happens when cooling an ideal Bose gas is that its density will follow the normal state until we hit the critical temperature at which phase 1 will develop and the gas will condensate into a phase 1 Bose-Einstein condensate. By turning around the equation that we just obtained, we can estimate the critical temperature, which then depends on the density and is given by kBTC is equal to n divided by 2.315 4 pi square root of 2m divided by h squared. Using the mass of helium-4 and the density of liquid helium, obtain a critical temperature of 2.17 Kelvin. This is exactly what you will find in experiments. The explanation of Bose-Einstein condensation in liquid helium-4 was one of the hallmarks in the development of statistical physics. Without any adjustable parameters, we could explain the critical temperature of helium-4 that exactly matches the experimental values. You should watch the BBC movie to appreciate the spectacular properties of this new phase of helium-4 called the superfluidic phase, characterized by a fluid that has no friction.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomenon in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.